Alright, here is your video lecture for Chapter 4, Section 1. Chapter is titled The Arrangement of Electrons in the Atom. But before we start talking about those electrons, we need to start talking about, or continue talking about the atomic model. We're going to get a little bit more current. Last chapter we ended by talking about Rutherford's gold foil experiment and how it demonstrated that the atom contained a nucleus that was a very small, dense, and positively charged piece of matter at the center of every atom, regardless of element. But, as I'm sure we can imagine, that Rutherford's model was incomplete. It was not incorrect, it was very correct, but it was incomplete. And so we needed to keep adding to this model in order to get a better understanding of the atom itself. What we're going to refer to in this chapter is the fact that in Rutherford's model there was no explanation of what the electrons were doing or how they were distributed around a nucleus. All Rutherford was able to conclude was that the electrons were outside of the nucleus, and that's about as far as he was able to go. So up until this point, into the early and mid-1900s, light was known to be an energy source, or should I say a form of energy, and it behaved like a wave. So up until that point and after that point, scientists began to move away from that sole definition of light, that it behaved like a wave. They began to investigate its possibility of behaving like both waves and particles at the same time. Now, electromagnetic radiation does act like a wave as it moves through space. Okay, and as it is moving through space, we refer to it as radiating outwards, therefore as a form of radiation. It is electromagnetic radiation, and it forms the electromagnetic spectrum. Okay, there's more to the electromagnetic spectrum than what we can see. What we can see we refer to as the visible spectrum, but there are lots and lots and lots of electromagnetic radiation that the human eye cannot perceive. This is a common chart that you might find if you went searching all the different forms of electromagnetic radiation. The major players, you have the gamma rays, the higher energy, move down a little bit in energy. You see the X-rays, move down more, the ultraviolets, then into the visible, then into the infrared, okay, no longer visible, then to the microwaves, and then radio waves, being the lowest frequency and the longest wavelength of all the electromagnetic radiation. Here I'd like to point out, compared to the entire spectrum, how small, compared to the rest of the spectrum, the visible spectrum is. It's very, very small compared to the entire spectrum itself. So up until this point, believing that light only behaves like a wave, there are two aspects of a wave. There's the wavelength, which is the distance between corresponding points on adjacent waves. So we can truly imagine this like a wave on the ocean. Okay, you have wave crests. The distance between crests of waves is the wavelength. We also have frequency. It's the number of waves that move past a given point per unit of time, and it's usually measured in hertz, which is one per second, okay, or second to the -1 power. And that's if you're at a fixed point, how many wave crests pass your location. So you're basically counting how many go in front of your face. And it was known that frequency and wavelength were mathematically related. Okay, C equals lambda multiplied by nu. So we have C, which is a constant, that's the speed of light, okay, equals lambda, this kind of funny looking Greek letter, which represents wavelength measured in meters. And we have nu. I know this looks like a V, but this is actually the Greek letter nu, N-U. And it represents the frequency of the wave. Here, the notation is seconds to the -1. Again, understanding how exponents work, that represents 1 over seconds. So it's 1 per second. So if you have a frequency of 1 hertz, that thing is happening 1 time per second. Now, when things started to get dicey was the investigation of the photoelectric effect. And this wasn't an observed phenomenon. It refers to metal throwing off electrons when a light was shone onto the surface of the metal. But it was found that not all kinds of light were able to eject electrons from the surface. Now, just understanding light or viewing light as a wave-like thing, it did lead scientists to believe that this shouldn't be the case. This is not what they should observe. That even given a very low frequency or very low energy light, that given enough time, right, given enough time for the metal to absorb enough energy, enough frequency, that eventually there would be enough energy saved up to eject some electrons because they're becoming excited and being launched out of the atom. But that was not the case. And so it was found that there was a minimum amount of energy per unit. Okay, the term that was coined here was a quantum, which is simply a unit, an amount. Okay, and in this context, it's the minimum quantity, the minimum amount of energy that can be lost or gained by an atom. So here we have chunks of metal. Obviously, these metals have electrons around them. And these atoms are going to gain energy from the light that's being shone on them. Now, they can't absorb any amount of light. There is a specific amount, the smallest amount of energy that can be absorbed. And if there isn't that amount of energy to be absorbed, the energy won't be absorbed at all. Now, if the energy can be absorbed, that will excite the electrons, make them move further away from the nucleus, because they have more kinetic energy now, and it's harder to keep them close to the nucleus. And then they can be ejected. They can be ejected from. They can be so energetic that they no longer feel all the attraction force from the nucleus that's overcome, and they leave the atom. Now, there were lots of scientists working on this problem at the time. One of them was Max Planck. Okay, if you say Planck, that's fine. And he established this relationship. The energy of that quantum, okay, that minimum amount of energy, is related or is equal to the frequency, all right, that's still the Greek nu, representing frequency, multiplied by a constant, which was established by Max Planck and is now known as Planck's constant, and it's actually one of the major fundamental constants of the universe. It's a pretty big deal. But notice that h there is a constant. Therefore, the energy or the quantum of energy of a photon, of a piece of a amount of light, is completely dependent on the frequency of that light. Okay, the more energy in that light, the more energetic that photon is going to be. I said this word photon. It was actually one of the words that Albert Einstein came up with when he introduced this idea that, hey, I know light behaves like a wave. I understand that, and I agree. But we have to admit that it behaves like a particle as well. And the unit, the particle unit that he came up with for light was called he called it the photon, and it's a particle that has no resting mass. It has absolutely no resting mass, but it carries an amount of energy. And this idea between absolute mass and resting mass is not something that we're going to go over in this class, but you just need to know that the photon does not have mass. That's as far as you need to understand. The energy of any particular photon, and it can be different, depends on the frequency of that light. Okay, it depends on the frequency of that light. The larger the frequency, the more energy that photon is going to have. The lower the frequency is, the less energy that photon is going to have. One of the ways we see how these electrons, okay, that are absorbing this energy, one of the ways we see these electrons behave came to us by observing what's known as emission spectra. Okay, now a little background on this. Using hydrogen, it's the most simple element there is, so it's a nice experimentum crucis for us. Now, up until this point, experimenters, they knew that if they took some hydrogen gas at low pressures, they put it in a vacuum tube and they ran an electric current through it, that it would glow in this kind of pink way. And there were other gases, other gases known. They could do the same thing and it would generate different colors, and it was fancy. It's the basis of neon lights. But for hydrogen here, it's the most simple one, so we're going to use it, and it has this kind of pink color right here. So here's a chamber, low pressure, that's hydrogen gas in there, and there's an electric current being moved through it. Now that pink glow is light. Realize that is light coming out. Those are photons being thrown off from the gas, being emitted from the gas. There is light coming out of that. And when that light is moved through a prism, you can see here that light is split into multiple channels, multiple specific channels. And what they do is they show up on a screen as individual lines, discrete lines, just like discrete quanta. It's these 4 bands of light that are known as hydrogen's line emission spectrum. So here's a picture of the actual line spectrum. So you take that glow off of the hydrogen gas, move it through a prism, and it will split into these 4 bands. Now, it's important to point out that at this point that particle idea of light wasn't fully in place. And so if electromagnetic radiation exists on a spectrum, smooth spectrum, we should see a continuous frequency, every band, all colors, no 4. There should be an infinite. It should be smooth transition. But obviously, that's not what they saw. Going back, they didn't. That's not a continuous color spectrum, and so they saw quantized, discrete color bands. And so this led them to believe that the amount of light, the energy of the light that was released from this hydrogen gas was relative to how excited the electrons were before returning to a ground state. Now here's some background definitions. The lowest energy state of an atom, is its ground state. The electrons have a low amount of kinetic energy. They're close in to the nucleus. They're not moving quickly. Now, if you add energy to that system, you're going to excite the atom, and that's going to represent, show itself as these electrons moving away from the nucleus, and they are now in an excited state. They have a higher potential energy than the ground state. Those electrons have moved away from from the nucleus. Now, keeping in mind this hydrogen line spectrum, this scientist named Bohr, he generated this model of the atom using those photon emission spectra, and he was able to explain or put forth an idea that the reason that there were discrete lines is because an electron, as it moved away from the nucleus, could only inhabit specific distances from the nucleus. It was not a smooth transition. It was more of a jump. It was like walking up steps as opposed to walking up a ramp. So if you were to add energy to that electron, it was not going to just smoothly go up a ramp. You had to add enough energy to that electron, to that system, so that the electron would jump up an entire step. And if you did not add enough energy to that electron, it would not move up an entire step, and it would not excite to the next level. So in this idea, the electrons can only move around the nucleus in allowed paths, which are now termed orbits. The energy of the electron is higher when it is in an orbit further away from a nucleus. Keeping in mind that image of a staircase, where in order to get further away from that bottom floor, you have to expend more energy. So if that electron is further away from the nucleus, that electron is in a more energetic state. So when it moves down back to its ground state, it will release more energy Okay, that is a higher frequency photon. Okay, showing a more energetic form of light, moving more towards the purple end of the visible spectrum. So, like I just said, when those electrons move from an excited state back down to the ground state, or to any lower energy state, it doesn't have to be all the way down to the ground state, the photon of energy is emitted from the atom. All right, that same energy that was absorbed by the atom to move into an excited state is going to be released when it moves back down to a lower energy state. This process is called emission. That's why we use the term hydrogen emission spectrum. Okay, it's a move from a high orbit to a low orbit. The term we use for taking in that energy and becoming excited is absorption. Okay, you're moving from a low state, a ground state, or any lower state to a higher orbit. Okay, so energy is needed to be put into that atom to move the electrons from the lower state to a higher state. And that energy is usually going to be in the form of light or any form of electromagnetic radiation. For you guys, what you're going to need to be able to do on a quiz and on the test, the energy of a photon can be directly calculated if you know the frequency of the radiation being emitted. And so what you're calculating is, let's see, we have this nucleus and an electron, a single electron. Okay, this is hydrogen, remember, it's just got one electron moving around. It's one proton in the nucleus. And a photon, some form of electromagnetic radiation or light, okay, it comes in, is absorbed by the system. It adds energy to the system, and that electron jumps to another energy level. Okay, it is now an energy level 2. If enough energy is added, it can jump another energy level, and again and again and again, as is appropriate to how much energy is absorbed by the system. Each time you supply enough energy to move the electron to another energy shell, that electron is going to be moving further and further away from the nucleus. Now, the energy of the photon emitted from an atom as the electron moves from an excited state back down to a lower energy state is going to be relative or dependent on how many energy levels that electron drops. Okay, this movement from energy level 3 in this diagram just to energy level 2 is going to release a certain amount of energy. If this electron were to fall all the way from energy level 3 to energy level 1, that is a larger drop. More energy is going to be emitted or lost in that instance, and the energy of that photon will be greater, meaning the frequency of light emitted will be greater. And so you'll see a movement from the red or low end of the visible spectrum to the purple or violet, the higher energy end of the spectrum. And in class, we'll talk about what kind of calculations we need to do using that C equals lambda nu and E equals Planck's constant multiplied by nu. We'll go over examples of that next time we meet. So bring your questions and be ready to do calculations.